Okay, so the program delayed a little bit, but Andrea will have 45 minutes as scheduled. So I'm very pleased that Andrea could make it and come. So Andrea is an associate professor at MOX, the Department of Mathematics in Milano. So he will present reduced order modeling and scientific machine learning, synergies and opportunities. The floor is yours.
Thanks a lot, Yvon. Merci beaucoup. Good morning to everybody. First of all, I feel very honored to be here and to give this talk. Before starting, first, acknowledgements to several people, in particular to the people you see on the left. So Nicola Rares-Franco, Simone Brivio, Nicola Farenga, and Matteo Tomasetto. Nicola is young researcher, Simone Nicola and Matteo are PhDs. Most of what I'm going to show is indeed due to their work. And I wanted to start also with the last slides, which I finished my last talk in Roscoe 2017. Acknowledgements also to grands hommes. We are, I think, on the shoulders of giants regarding giants and giant people. We can indeed rely on so many tools and so many methods, and we have seen already yesterday and this morning how many concepts we have. The question I would like to focus on is whether scientific machine learning and reduced order modeling somehow can create a kind of, not just a winning combination, but maybe a natural synergy. And in particular, how do deep learning algorithms impact on accuracy and efficiency at the same time? So I will somehow follow some of the story of the last 7-8 years regarding the developments we have been focusing on, trying to, show at least 3 instances on cases where indeed theory and applications go together somehow. If we're back to 2017, this was somehow there is a screen that is a bit on top. I don't know if you can move a little bit here, the screen. Maybe when they're cut. Anyway. No? Okay, thank you. Great. This is the kind of problem that motivated us to look for different approaches. This is a problem arising in cardiac electrophysiology. This is a nonlinear steady reaction diffusion problem. We just had 3 parameters, so not so many. And because of the huge variability the solution shows when you tune those parameters, this is a very idealized situation of the kind of, electrical potential wave propagation on the tissue. Of course, we experience very different behavior. So we were dealing with classical reduced order modeling techniques at that time, POD-Galerkin methods. And no matter if you also relied on local reduced bases, for instance, also coming to the last question, well, the reduced space was not so reduced. So we were able to build spaces of dimension about 200. The solution is good, the accuracy was fine, but the efficiency, of course, was starting to lack. And all we needed were better ROMs, indeed. Because even in presence of, local reduced basis spaces, for instance, well, POD-Galerkin ROMs are not well suited, we know, to problems that, for instance, features these coherent structures that propagate over time. And moreover, we had other difficulties to face. Of course, the reduced dimension was not as small as we wanted. Hyper-reduction techniques are costly and intrusive. And even more, all the variables that are involved in the full order model must be accounted in a reduced order model if you rely on these techniques. And this is somehow, the years-long journey that I would like to show in this presentation, starting from some tools that have been already mentioned yesterday, for instance, showing how, indeed, some building blocks, fundamental building blocks that we were used to, involve in the construction of classical reduced order models, physics, geometry, and dynamics, essentially were taken out during the construction of non-intrusive reduced order models like POD neural networks or deep learning-based reduced order models. So somehow we wanted to go to the data-driven side, say, but in the end, we realized that we needed, of course, to inject back, to take into account back building blocks like physics, geometry, dynamics, and if time allows, also sensor data. This is the picture we all are familiar with, building reduced order models using, say, POD and Galerkin projections. Essentially means to rely on two tasks. We need to learn, say, the reduced trial manifold. How do we want to express our solutions? And this is a matter of dimensionality reduction. And then we need to give a suitable recipe to write and then to solve the reduced problem or the reduced dynamical system. And this has been done, of course, by using Galerkin projection, for instance. This is the picture that we can use to, say, see the two different tasks. So starting from a time-dependent nonlinear problem, what we get as a reduced problem in the orange block is indeed, say, physics-based, is a physics-informed, the best example of physics-informed technique we may have. So a reduced dimensional dynamical system where essentially a high dimensional data of dimension nh on the left, the green, vectors have been projected onto a low dimensional space of dimension n. V transpose and V are two matrices if we rely on linear techniques like proper orthogonal decomposition. Of course, this can be expensive and intrusive. For instance, we need to rely on upper reduction very often. For large n, the Kolmogorov and width show as low decay, so problems could be not reducible using this framework, and all the variables that were included in the form must be included also in the ROM. And this was, for instance, an application. These are shallow water equation solution on the globe. This is a case where indeed you can see quite easily this slow decay of the singular values when you compute different solutions of this problem for different parameter values. So first attempt has been due to Janne Staven and collaborators. For instance, you could replace the projection by means of this neural network that from the parameters and possibly also time somehow lead you to the reduced or latent space. So this is the POD plus neural network. A feed-forward neural network is used to approximate the POD coefficients, but of course we also have alternative options, for instance, Gaussian process regression, or also operator inference, and all the work due to Karen and collaborators. A simple example, just to see that indeed few milliseconds are required in this, say, case of an hydraulic pump to, for instance, assess the behavior of such a machine regarding, say, parameters such as the flow rate. Very often in industrial collaboration, you don't have access to code that you can, say, open, so you only have access to data, and indeed, this was the first attempt of using, say, non-intrusive techniques, conjugating, say, linear dimensionality reduction in neural networks. Of course, say, if we also want to look a bit more carefully to this, we can say something because the approximation the approximation error can be indeed split. It's just a matter of Pythagorean theorem on two terms. One is the projection error, the yellow one, and this is, say, controlled by the construction of the space, and the second is the error that somehow we introduce when we consider this phi map. Phi is the neural network that tries to approximate the projected version of this solution. And of course also the reduced error can get arbitrarily small, designing suitably constructed neural network. Sometimes you can also be even more accurate than POD-Galerkin because you can somehow approximate directly the approximation of the solution onto the POD space. Second, stage, why not to replace also the linear dimensionality reduction that was due to POD before with an autoencoder. E and D are the encoder and the decoder, respectively. Again, we have another neural network that from the time and the parameters goes to the latent space. Now we have three neural networks, and this is what we called DL-ROM a few years ago. And it's a matter of training now three networks. You can train them together or separately. Several approaches are available. Essentially, you need to reconstruct solutions, the first, say, term on top in the loss function, and you must, of course, also connect the parameter space and the latent space. In this way, we can keep, indeed, the latent space dimension extremely small. We can query this model at every time, so we essentially have lost the notion of time as time in dynamical system. This is totally non-intrusive, so we can avoid hyper-reduction, and we can also overcome the difficulty entailed by this low decay of the Kolmogorov width I mentioned before. We started by applying this, and then we started understanding why indeed it was working. And this is also common to other strategies I'm going to show. This is a similar problem to the one I showed before. So again, there's no linear reaction diffusion equation where the parameters are related with the lack of the conductivity in the tissue. This lack of conductivity can move around the domain, and this makes, say, this front to be approximated a bit weird to approximate because of the dependence on the parameters. So we have two parameters, essentially the center of a small Gaussian that can move around the domain and time. And for such a problem, of course, the space is not that big, so 4,000 degrees of freedom in the finite element space are not a big problem, for sure. But the comparison is that just 3 dimensions in the latent space are enough compared to the 87 dimension of a POD space if we just relied on a single global basis. And this also impacts on the computational time. A slightly more involved case where we have this re-entry phenomenon. Here the situation would be even worse for POD because more than 1,000 of basis functions would be required to approximate correctly this pattern, and on the other hand, the DL-ROM takes much less, both in terms of time and latent dimension. So, talking about this after Albert Cohen, of course, is a bit embarrassing, but I will try to do my best. So just a few slides to somehow try to understand what is going on, because if we start from the notion of Kolmogorov width in the linear case, well, now, as Albert was showing before, we can indeed rely on one of many, say, nonlinear analogs of nonlinear Kolmogorov width, and psi and psi prime are indeed the encoder psi prime and the decoder psi, and this is a notion, as we have just seen, strictly related to the topological properties of the manifold. And we started by, say, quantifying how an optimal compression would work. So if this n min is the minimum value of m for which we get 0 there, so a kind of theoretical optimal compression reached, we have been able to characterize this minimal latent dimension as a function of the number of parameters we have. And indeed, say, first results that we proved 2 years ago was that we can bound this minimum dimension from below and from above by P, and P is the number of the parameters we have in our parametrized PDEs. And even more, if we rely, for instance, on simple classes of problems like, say, diffusion, advection, stationary, so linear elliptic PDEs, second-order PDEs, we can also show that, say, this minimum latent dimension is indeed equal to P. Of course, there are several, say, assumptions and several tools behind. I wanted just to highlight the main achievements. And even more, we started also digging a bit more into the construction of these architectures. So the main questions we always face is how to design these architectures, how to design the encoder and the decoder. And in this case, if epsilon is the kind of threshold we want to reach in terms of accuracy, well, first of all, we can highlight two sources of error, essentially as we did before for POD-NN. So a kind of reconstruction error on the left, ER, and a kind of, say, error due to the fact that we have to approximate, say, in the latent space, the relation between the parameters and the latent coordinates, EP. If we put these two contributions together, indeed, we prove that we could indeed assess how many layers and how many neurons we need to take into account if we want to reach this accuracy level of epsilon. So psi and psi prime could be somehow tuned and built also with an eye on the level of accuracy we want to reach. I don't want to go, of course, into details here. All the details are contained in the papers. Third issue we tried to face at a certain point was, well, first of all, why not to put together the two good lessons that we have learned so far? POD is optimal among linear dimensionality reduction techniques. The autoencoder works pretty well. At a certain point, we had to face high-dimensional problems regarding the dimension of the snapshots data. So NH was no longer 4,000, but a million. So in this case, we found pretty convenient to first perform a kind of linear dimensionality reduction in a big space. This is not our finely reduced space using POD. And then considering the autoencoder architecture from that point, and this was the so-called POD-DL-ROM, we were able to get faster training compared to a DL-ROM only. And then there are other, say, technical issues. Again, I don't have time to go into detail here, but regarding the pre-training way of, say, training the architectures, for instance, there are several strategies to do this. And this allowed us to face problems like this. This is a more, say, involved version of the problem before. So the electric potential, again, these were results, say, in collaboration with Alfio and all the crew behind the IR project a few years ago. The electric potential on a ventricle and then on an atrium now could be computed, say, in less than a second compared to the 3 hours or the 2 hours that a full order model based on finite elements would require. So essentially, we're, say, almost at the level of being able to perform real-time simulations if you think about the scale of the physical phenomenon here. And the same for fluids. This is the typical benchmark in fluid dynamics. So the flow past a cylinder, just 50 minutes of training a few years ago on a not on the best GPU. Available at that time allowed us to get solutions for new Reynolds number here. The Reynolds is the parameter in much less than a second. And the same here for the flow, for the blood flow in a cerebral aneurysm, where you can, for instance, play top right with the flow rate. So you can assess, for instance, how the fluid flow into the aneurysm behaves if you are at rest, for instance, or not. So parameters are related to the flow rate. And also here, the speed up with respect to the full order model was order of 10 to the 5, getting, say, computational times less than a second, say, and errors, again, of the order 10 to the minus 5. By the way, we are not training these models on 10,000 GPUs. And this was also another, I think, following other discussions with several people, this is another reason, in my opinion, behind the developments of methods, having not access to huge computational resources compared to what, say, many big players now have, somehow has forced us, and a lot of people in this room, of course, to look for clever solution from a mathematical viewpoint and computational viewpoint, I think. So far, everything was purely data-driven. So we got data from the full order model, and then we trained networks, okay? Nobody guarantees that the fluid flow in the previous slide is incompressible, for instance. In practice, it is. But we didn't have any way to, say, constrain the fluid to be incompressible, for instance. So our first extension was in the direction of physics-informed DL-ROMs, essentially borrowing paradigms from the physics-informed neural networks. We tried somehow to mitigate also the possible effect of data scarcity through physics-informed operator learning. So this is an approach very similar to the DeepONet idea, where now we essentially have, say, again, an architecture as before, so a POD reduction, an autoencoder, and then, say, we needed to rely on a space-continuous formulations because now we need to compute residuals of our equations, and the residuals means derivatives. So we need to be able to compute derivatives and then to add to the loss function, essentially, a new term that, say, allows us to take into account the equations of the problem at hand. And this is somehow how the loss functions now looks like. The green part was already there because we have, say, the two terms as before, reconstruction of the data and then learning of the operators. But now we also have, for instance, the residuals on the domain and on the boundary to encode all the knowledge we have about the strong formulation of the PDE problem. And I don't want to go into detail, but essentially training these architectures becomes a bit more, say, involved because you cannot train everything at once. You need to pre-train a term, freeze it, and then to train essentially the branch net with this physics-informed loss function, and then go back and do a kind of final train, a final fine-tuning of the whole. Results. These first results are on a simpler problem, parameterized Darcy equations. Now the comparison at the bottom left is about errors. So we have two parameters, mu1 and mu2, and these are errors plot. The magenta window is the training range. That is the range where we collect these snapshot data. But of course, we know the problem we are solving. So we try to extrapolate the solution out of the training range, something that we didn't do before in the results I showed. So essentially, if we rely just on a, say, POD-DL-ROM as before, and we try to query our network to compute the solutions out of the training range, well, the solution would be completely nonsense, the left solution here. If we are able to inject knowledge about the equations we are solving also out of the magenta box where we collected the training data, essentially we can indeed restore, say, good predictions and good errors. So if you compare, say, the errors that you have on the right and that, say, half part on the bottom the slides, you can see that the errors doesn't grow so much when you exit the training range. And the same is visible here. We collected data till 1 second regarding these simple, say, benchmark and Navier-Stokes equations, and then we try to extrapolate to forecast the solution until time equal to 4. Well, in light blue, you have the purely data-driven techniques. The errors goes higher and higher, and the physics-informed DL-ROM indeed allows us to keep the errors, say, under control. This was a first possible extension. Of course, the architecture becomes much more heavy to train. Second extension, geometry. So far, our data were columns. We had vectors, and even if I didn't mention explicitly here and there, also a bit more involved architectures appear, convolutional layers, for instance, in neural networks, and even if our geometries were not squares or rectangles, well, convolutional layers were working pretty well. Now, the point is that if you have very involved geometries, or in general, if you want to, say, take into account information about geometry, how to do that? We proposed two options. The first was, I would say, a quite simple trick, is an empirical trick. We gave it this name, mesh-informed neural networks. Essentially, we started thinking about, say, the encoding and the decoding process as the, say, coarsening and refining strategies that you have when you play with, say, mesh refinement, for instance. All our data are indeed living on computational meshes because we come from finite element approximations. So the idea is, why all the nodes on the mesh have to, say, talk to all the other nodes? In other words, why all the, say, neurons of a layer have to be connected with all the others? So how, why not to, for instance, impose some sparsity constraint to dense layers in networks so that we prune the architectures by setting a lot of connections essentially equal to 0. We want, for instance, if you look at these pictures, we want to turn from the left situation where all the vertices talk to all the other vertices in the new refined mesh. We want that, say, each node is in connection only with the neighbors. Okay? And this allows us, for instance, to sparsify a lot the matrix of the weights. And this means that we need to look for say, minimum for minima in less dimensions, and we can make the architectures less heavy, sparser, and the training also much more efficient. So we prune all the connections that somehow we don't want to include, and this is what happens. By the way, you can also play with, say, more involved notions of distance, because, say, here on the right, you can see examples. This is a two-dimensional slice of a brain. Here you have, for instance, situations where, of course, 2 points that are close in a Euclidean sense are not close, say, because essentially you need to consider all the path to, say, reach the 2 points. This is a case, for instance, of approximations where this mesh-informed notion was working pretty well. On the left, an easy case, there is not this issue of dealing with complex geometries, but on the other hand, you can see that, say, the memory requirements for the same architectures requiring to deal with the same data must be much, much less, and this also an impact on slightly better performances regarding training and test errors if you compare a dense network and a mesh-informed notion. Further step in the direction of, say, playing with geometries, since we already dealt with this, say, continuous, formulation before to handle residuals. Well, what we try to do is somehow to adapt the POD basis to the new geometries. This has been, say, a crucial bottleneck for many reduced order modeling techniques. Every time we had to play with different meshes, we were no longer able to put together basis functions because of the fact that, say, the degrees of freedoms change, and then we can no longer realize this kind of linear superimposition of modes. But now we have neural networks, and why not to use neural networks to learn how to adapt the basis functions to every new shape? This is, in a sentence, the idea. So we relied on a space continuous framework as before, and we made everything depending on a vector of parameters. Essentially, the architecture is as before, but now that magenta block, that is, again, a POD block, because we have a set of n basis functions that we need as, I would say, lingua franca to connect all our simulations. Well, those bases can be adapted to the new geometry. Essentially, we can indeed, say, consider the fact that now this set of basis functions is not available in a closed form because of the possibly, say, involved dependence on these geometrical parameters, and we can indeed approximate them by neural networks. Again, the details, if you're interested, are on the paper. The examples we played with, not as difficult. This is the flow pasta cylinder, where we have different cylinders. The positions can change. The diameter of the cylinder can change. The topology cannot change in this case. And this is an easy heat transfer problem, where you have a fluid flow modeled by Navier-Stokes equations in this heat exchanger, and then you can modify. This is just one instance of what you can get in terms of, say, few parameters that vary the geometry. Those rectangular, say, portions can move, can be squeezed, small or large. And this, by the way, also opens up a connection with the world of operator learning, because this transition from discrete to continuous could be also understood using a parallelism, I think, between the POD neural network world and the DeepONet that somehow can be also seen as two sides of the same coin. Again, also a DeepONet allows to realize a kind of linear superimpositions, and also DeepONet somehow use a kind of separations of variables approach, and this is very equivalent to the representations that we saw, but now the basis is no longer fixed as in the POD-NN case, but is learned using networks. And this would be somehow the way in which the architectures would look like if we want to stick on the same kind of framework that we had before. I want to jump on dynamics, because so far all the time-dependent problems were indeed solved as not dynamical systems. We can query our networks for every time. This means that we can also compute the solutions at the final time of our time horizon, but of course breaking the causality principle, for instance, of the time-dependent nature of the problem. We propose two possible approaches. One is, say, more, I would say, empirical, relying on, say, sparse identification of nonlinear dynamics, and the second is pretty new. So if Yvon is going to run another chair at the Collège de France in 5 years, maybe finds this paper interesting, and maybe we can somehow consider the time-dependent version of this story. By the way, the first attempt we considered was replace the neural network that we have in the latent space by any time-dependent or time-aware network, recurrent networks, long short-term memory networks. It works, not so well. It works not so well because, for instance, you can extrapolate on an easy problem like the flow pasta cylinder with Reynolds number varying. Again, we have parameters that change. We want to predict the solution for new parameters, also out of the training time range. But the extrapolation is good, not so far from the end of the training range. Much better results were indeed obtained if we consider, say, a notion of latent sparse system. So why not to learn the kind of dynamics that is fulfilled at the latent level? Several approaches are available, starting from linear dynamic mode decomposition, for instance. Here we relied on a sparse identification of nonlinear dynamics framework, also due to the collaboration with Nathan Kutz and Steve Brunton, started a few years ago. This is a compact way to combine together pieces that you take from a dictionary of functions, enforcing sparsity on that vector of coefficients in order to have just few terms, say, also to have a look at the kind of model that you get. In a slide, essentially, this is a bit the idea. So you have data regarding, say, your dynamics. This, of course, was born before this, say, autoencoder plus SINDy. We are just, say, starting from the autoencoder plus SINDy approach, but the SINDy approach is, of course, comes before. The idea is to take, say, as description of the latent dynamics, a kind of linear superimposition of user-defined functions. This theta z is a huge bunch of functions, and then solving this sparse regression problem, we enforce, say, many of those parameters to be zero, for instance. And we can inject everything in this, say, dimensionality reduction by autoencoders approach, and we can, for instance, say, minimize a loss where we have all the contributions. So an autoencoder loss, this sparse regression loss, and then we want that the two words, we have data at the high fidelity level, but we are working at the latent space, the two words must be compatible. This is the situation for the problem before. Now the idea is that you start by different initial conditions, x0, and different values of the parameters. We can encode now everything to this latent space. And now at the latent space, we have a nice dynamical system to integrate. This is small. We can rely on whatever time integration scheme we want. And this means that we can march in time and then get the solution at the latent level and then reconstruct it back to the high fidelity. And for instance, on the same case, we were able to reach the 50%, say, out of the training time range accuracy compared to the 13 that we had before. And we were also pretty able in this case to follow the bifurcation diagram regarding the critical Reynolds number at which this bifurcation occurs. Now, some words about a new approach that somehow allowed us to also do some math and better understand what is going on. Essentially, we wanted to better understand how all the possible errors that we are introducing impact on the accuracy of the final solution. It's a matter of, say, combining not only neural networks, but also numerical discretizations in time. The notion of latent dynamics model uses a much more general description for this function fn. Before it was a linear combination of functions. Now it's a neural network. So somehow it seems that we want to find something that is more general but less explainable, because before we wanted to explain what was going on. Now with the neural networks there, the situation is as weird as before. Yes and no. I would like to try to convince you that this could be also a good option. We want also to preserve the training accuracy on finer time discretizations employed during testing. This is another problem that we had always faced. The time discretization that you choose when you compute your snapshots data somehow dictates also the time stepping that you can use when you compute your solutions. Here we wanted somehow to train the architectures on a given time step and then maybe be able to also explore what happens at different, maybe smaller time steps. Somehow reaching a kind of continuous in time approximation. The desiderata are these three. Well, the third is the easiest one. We want still to preserve a kind of initial value problem structures. We like solving initial value problems, and this is something we want to keep on doing. So we want only to have the initial solution, the initial conditions, and then start from them to compute all the, say, behavior of the system. Causality. We want, of course, that the approximation at the next time step depends on the previous step. And then this zero-shot time resolution invariance. In other words, we want that the approximation error between the FOM and the ROM is almost constant if we refine the temporal discretizations. Now, the pictures on the left somehow shows this, because we have two words now, the high-dimensional word and the latent word. And then we have concepts that are, indeed, different levels of approximations. In blue, this is the full-order model. This is time continuous. This is our, full-order model code that we have. Then we start by, say, including a latent dynamics model approximation, the green one, and the latent dynamics UN in the latent space, psi and psi prime as before, encoder and decoder. Then we have some errors that arise from the numerical solution of the latent dynamics, because if the latent dynamics now is a dynamical system to solve, we must integrate it, and we must keep also the errors we introduce at that level into account. And then, even more, that neural network must be trained. So this means that we also have, say, errors to take into account regarding the fact that we need to train a neural network and to find, say, the best expressions that somehow allows us to match the data that we observed. So we have these words that communicate at the high-dimensional level at the reduced level. We can skip this. What we did, I don't have time, I just have time to show some results. What we did was first analyze the error sources and derive also stability estimates. We could prove stability estimates regarding this. We wanted also to address, say, the impact of the numerical errors when we solve these latent dynamics. All the errors that we have at the latent level, of course, reflect on the final approximations that we get. So we want to be able to control the errors in the latent space and be sure that they do not explode when we go back to the high-dimensional space. And then we also derive the time-continuous approximations that result in a learnable context where indeed you have deep neural networks coming into play. And we were, in the end, able to characterize convergence, consistency, and zero stability results for the latent dynamics and showing how this impacts on the accuracy of the final solution. At the end of the day, Lipschitz requirement on these projection reconstruction maps are a key ingredient. So the latent dynamic model could be seen as a tripole, psi, psi prime, and Fn, so that, say, this minimization problem is solved. So we are looking for a way to express, say, the dynamics at the latent level. UN is the dynamics at the latent level. Of course, this is more a theoretical way of seeing the problem, because we must convert this to an empirical version where we have snapshots data and then networks to train. If this happens, well, the dynamics UH can be approximated by, say, decoding the latent dynamics, what you have in the parentheses, essentially. But to reach this, essentially, we had to put together three different pieces. Starting from the full-order model, well, we have this time-continuous version of the latent dynamic model. We need to discretize it, for instance, using Runge-Kutta methods. But then, what we indeed want to play with is a learnable version, so that delta LDM theta is a learnable version that, by the way, we learn directly by taking snapshots from the full-order model. So essentially, the results that we wanted to prove was a kind of, say, good behavior of the learnable model compared to the FOM, but the kind of path that we had to perform was through these three steps. At the end of the day, you train everything by minimizing a loss function where you have for mu j values at times tk data, and you want that the latent dynamic model in the trainable version, say, is as close as possible to this. So the usual training. But to explain how to design these networks and how they work, we need to take a much longer path. Just a couple of slides of results. This is indeed, say, the behavior of the errors over the delta t, assessing somehow this time continuity property for two cases, Burger's equation on top and advection diffusion reaction at bottom. using indeed two methods, Runge-Kutta 2 and Runge-Kutta 4, and indeed we are able to indeed restore the expected, say, convergence rate. And somehow, say, the approximation error that you have on the plot between the FOM and the ROM is almost constant as your delta t, say, becomes smaller and smaller. Second, kind of zero stability property, because we can also show the robustness with respect to initial value perturbation. We perturb a little bit, say, the latent dynamics, and we observe what happens at the high dimensional level. And again, for Burgers and the advection diffusion reaction problem over the whole time range for, say, perturbations of increasing size, say, the errors are kept under control. What is even more nice is this slide, in my opinion, because you have the two cases, Burgers 1D, X and T, and then this 2D advection diffusion reaction problem. Of course, the physics is not that difficult, but the nice thing is that at the latent level, somehow the architecture is learning a kind of pixel version of the true dynamics. So if all these pieces are designed properly, at the latent level, you can clearly see what the network is trying to learn. The network is trying to learn a kind of coarse, super coarse version of the phenomenon that you had somehow in your data. And this doesn't happen always, say, for any architectures. And also here, as soon as, say, your data somehow show this kind of behavior at the latent level, say, you can see somehow a reminiscence of what was contained in the physics. And this also regarding, say, extrapolation with respect to time, because we can, say, compute forecasts, say, in the future, and the parameters. Now, if you still have 5 minutes before a coffee, last part, because this also has, in my opinion, connections with, say, recent achievements, the PBDW method by Yvon, for instance, or other techniques like the GAPI POD and many others. How to take into account knowledge about sensor data. So far, our inputs were just parameters. So we have a vector of parameters, and then we want to compute the solution. What if we also have access to sensor data? Many cases, many applications offer us this possibility. This is done in collaboration with Nathan Kutza, and Matteo Tomasetto was indeed the main actor behind this. So essentially, so far we played with autoencoders, encoder and decoders, and the idea, starting from the architectures they introduced, was to bring this at the level of reduced order modeling by letting also input parameters come into play and then more cleverly, say, train everything. We assume to have sensor data, few sensor data over time, and also access to, say, high fidelity data. The idea is to somehow learn two networks, one that takes into account the time dependence of the sensor data, tries to learn a latent representation of those data, and then a decoder that allows us somehow to reconstruct the full field starting from the say sensor data and their representation. The training loss is as simple as that. We have two say networks, one that takes into account the spatial, say, dependence, the decoder, and the other that takes into account the time-dependent nature of those data. And by the way, this reminds us, say, our first class in PDEs, kind of separation of variables approach. And this also is a bit the way we try to motivate this, because if you go back really to the first class in PDE, so a 1D linear PDE, of course, and you look for solutions in a separated form, t times x, well, you get two problems. One is say, dynamical systems, and the other is an eigenvalue problems. Of course, they are related each other, but say this idea of separating variables, of course, is already contained here. Now, how to, of course, get the solution? Well, the solution, at least for linear PDEs, is a linear superimposition since Fourier of modes. The coefficients an are the missing blocks that we need to compute. Well, how to compute them? Well, say, during our first class in PDEs, some master told us to essentially take an initial conditions and then to compute essentially the projection of the initial conditions onto onto the elements of the basis. But why not to consider, rather than the knowledge of the whole solution at every point in space at one time, the knowledge of maybe the solution at one point in space, or few points in space for the whole time? So somehow, why not to consider a kind of sensor value problem rather than an initial value problem? So in this way, and this is somehow what motivates the fact that the knowledge about few sensors indeed allow us to reconstruct the solution. If here we force the solutions to be equal to what we know on the left, that given positions xs, that by the way can also be moving sensors, this is another way, for instance, to close the problem. This was somehow, say, a one-slide rationale behind this idea. Of course, the situation is not as simple because our problems are nonlinear, but the architecture somehow would like to mimic a bit this, because we start by, say, high-dimensional states now, and h is again the dimension, and then sensor measurements that live in a much, much smaller dimension, and s. And apart from some, say, pre-processing in terms of padding and lagging of those data, we need to take those data as chunks and then give them to a long short-term memory network to learn this latent representation. Essentially, we took data in chunks, and then we try to, say, learn this. So offline, on top, we have different parameter values. Take the Reynolds number for these fluid flow problems, for instance. And for the training couples, you have sensor data and full field. Online, we want somehow to predict the state by having access only to the sensors for the same time window in which we collected sensors before. Of course, we could also try to extrapolate, say, much farther in the future. This for a new parameter value. And if, say, your data here are too big, again, the lesson before, a POD space could be a good strategy to make this decoder network somehow much smaller and easier to train. And by the way, training decoder-only architectures is much, much easier than training an autoencoder, also in terms of, say, hyperparameter tuning and all the other, say, steps that usually you take into account. Results to finish. This is a Kuramoto-Sivashinsky problem, time and space. This is a 1D problem. We have two parameters, viscosity and frequency of the initial conditions. The reconstructions are very accurate, and we use this test case also to investigate a little bit, for instance, how many sensors or where to put sensors. Of course, there are positions where it is nonsense to place sensors. So if you put sensors, say, far from the portion of the domain where the physics is taking place, of course, this will never work. But few sensors are enough. If you look at the right plot, for instance, 4 or 5 sensors already give you very good accuracy, and it would be super nice to prove results about how many sensors in this respect, given the difficulty of the parametric map that we are trying to approximate. This is still an open question. And then on the left, how long you need to take these chunks in time, and apart from, say, choices that do not make too much sense, so simple time steps, the one on the left, say already 10 or 25, say, time steps are fine. Again, how much sensitive is this regarding to the noise level you have on the data on the right? If we train, for instance, different models, we can see that indeed we can also be a bit robust regarding, say, possible noise. And then on the left, which are the best position where we need to put the sensors. Of course, the situations that is on the diagonal means that the two sensors coincide. This doesn't make sense, apart from some choices that are due to the particular structure of the solution here. Essentially, the plot on the left is telling you that, say, many possible positions are indeed fine. Another result, these are Navier-Stokes equations in a box with the 3 cylinders that rotate, and then you have a scalar that starts diffusing and be transported in the fluid. So this is a couple problem because we have a fluid plus an advection diffusion problem with just 3 sensors that can be fixed or 1 sensor that can move. We can indeed, for any possible choice of the 3 angular velocity of the cylinders, for instance, reconstruct the solution here. And even more, we can also say avoid to know a priori which are the parameters, because now we have the sensor data that come as input. So this is the case, for instance, of the fluid flow past a profile that depends also on two geometrical parameters where, say, we don't have, say, dramatic differences in terms of parameters, so we can play with the same mesh. This doesn't cause a problem, but nevertheless, you can, say, change a little bit the shape of the profile. You can change the inflow intensity and also the angle of attack, and you can somehow indirectly also infer about the value of the parameters because you know, say, the sensor measurements. So somehow is a kind of integrated parameter estimation, at least for these cases. And this is, for instance, a case in which, say, the inflow profile alpha here is changing because of this angle, and somehow you can also quite easily follow. And last but not least, we try to compare this with other techniques, also by us, the POD-DL-ROM or the POD-NN. At the end of the day, what we realize is that knowing sensors matter a lot, because we were able to get much smaller errors compared to many other surrogates. But of course, say, the condition here is to have access to, say, a further piece of knowledge, so the sensor measurement. Somehow, if we have access to this information, in addition to, of course, snapshots data, we can do better things. With this, I would stop by concluding that, of course, starting from the techniques we were relying on, of course, the situation is much more crowded. This is, I think, the kind of feeling that we experience. There are so many new techniques and so fastly appearing that is becoming more and more difficult to follow this. I think that we should say, at least that to the best possible extent, to exploit for sure the knowledge about the problem at hand. To be able to analyze, again, to the best possible extent, the mathematical and the numerical properties of the strategy we propose, and to explain why and how they work, to rely, why not, on classical, well-established, often easier paradigms, and also to connect methodological advances, I think, to challenges that are appearing everywhere in applied science and engineering. With this, I stop. Of course, join us in Milano for the Model Reduction Conference. Small advertisement about this, first week of November. And thank you very much for your attention.